Okay, good evening, everybody. Welcome to the session. This session is SRV373, Building Massively Parallel Event-Driven Architectures. This is a repeat of the session on Monday. My name is Amit Kulkarni. I'm a product manager on the AWS Serverless team. And it's 6:15, so I know I'm probably standing between people and the cocktail bar, so it's a very dangerous place to be. So we have about an hour's worth of content here. And the two key parts to focus on in this particular session are in the title. They are event-driven architectures and massively parallel. So this talk is all about how do you build scalable event-driven architectures. And so basically, we are going to set the stage on what we talk about when we talk about modern serverless applications. This is a 300-level talk. So we are not going to go deep into what serverless is. We expect sort of all of that. You guys to all know that. We are going to talk about what are the various concepts when we talk about event-driven applications. How do we look at architectures and various parts of it? And then we are going to go deep into three main areas of an event-driven architecture: the generation, routing, and processing of events. And then we're going to look into what are some of the key considerations in each of these areas to focus on. Finally, we're going to talk about, we will have Mick up here from Mapbox, and he's going to talk about their architecture from one of our esteemed customers, Mapbox. And then we're going to wrap it all up. So with that, basically, these are some of the 4 key tenets we think about when we look at serverless applications. And with using these tenets, we bring products and services to market and make sure that customers are able to develop agile, serverless applications, take advantage of elasticity of the cloud, and be able to get the lowest TCO when they're building these applications. And so basically, today, building serverless applications at scale is the new norm. Here are some examples of customers. FINRA processes 500 billion transactions, stock trade validations every day. MLB, Major League Baseball, processes petabytes of data using serverless technology. So these are some of the examples here. And a particular example of interest is financial engines. It's a financial services customer. And what they do is they are basically advising their clients. They manage close to $2 trillion of assets. And they basically have a solver that they have sourced from a third party. And they are trying to evaluate portfolios of customers and trying to give them, find optimum advice for individual portfolios. And so if you look at them, they've been able to take this and build it at scale to go to several 100 million requests per month, up to 60,000 requests a minute. And while doing so, they have realized the benefits of serverless by reducing their TCO by 90%, or over 90% actually, while basically building this highly scalable, reliable architecture. And so what does it take to actually go build such a serverless, high-scale architecture? Right? And it starts off very simple. The core concepts here, there's an event source, and the event source basically signals something in the real world that changed. And there's a function that processes it, and then the function can interact with other systems. And basically, the change in the event source can basically signal a change in state of data, like a file being dropped into S3. Or it can be an endpoint being invoked by an API call. Or it can be a change in the state of a resource, like an EC2 instance being live. And then your function can be in any of these languages that are out there, and it can now take action on that event. So now the question is, like, what does it take to basically take such core concepts and then build a massively parallel serverless architecture based on that? And so the key thing to think about here is, in order for you to scale to really, really high levels, you need to think about it upfront. And one of the sayings is that you need to engineer for the bottlenecks. So as we look through various parts of a serverless architecture, we are going to look at what are the specific considerations in each of these areas that you need to look at. So let's first go through components of our event-driven architecture and look at each of the concepts in there, and then evaluate what are some of the considerations in each of these areas. So basically, there are 3 parts to our event-driven architecture to analyze. There is the event generation portion that basically talks about what information are you emitting about a specific event. There is the routing part of the architecture, which says, how do you get the event that has been generated from the source, the event source, to the event processor, which is, for example, Lambda. And then how do you take action on that event, right? So it's the three straightforward parts. And in each of these components of the architecture, you have a variety of choices in terms of the AWS services that you can use. So in the event generation, you can have S3 generate an event if you drop a file in there. And there are several other such event sources. And one of the event sources that is not on there, but is still quite relevant for this discussion, is you can generate your own events. You can emit your own events and invoke Lambda functions from them. So that's also one of the things to think about. Event routing, the services like Lambda event mappings, SNS, SQS, and we're going to go a little deep into each of these services a little bit later. And then you can process these events using either Lambda functions, or you can run Fargate containers serverlessly in order to process these events. So now, in each of these areas, there are different considerations. So when you look at event generation, you have to look at payload. What is the size of the payload? What goes inside the payload? Whether the payload itself contains all the information about the event, or are you going to put a pointer to the actual data in that event? And then should the event be persisted, or should it be all inline? So we're going to go a little deep into this area as well. When it comes to routing, you want to think about what is the mechanism by which the events get to the event processor, whether they are delivered with a certain number of certain considerations in terms of whether they are duplicates, whether they are delivered in a certain order, whether your application is resilient to handling duplicates, whether it can handle events out of order, and then what is the retry semantics that goes into it. Finally, when it comes to building applications for scale, you're going to look at what is the overall throughput you can achieve by virtue of the events routing part of the architecture, as well as what is the overall sort of batch size and how do the events get batched from the event source to the target. When it comes to event processing, there are all these other considerations in terms of what is the most parallel you can go in terms of concurrency of processors. What is the rate at which you go from steady state to the top of the ramp? What does each individual function take in terms of its duration? What are the semantics when the function succeeds and fails? And then what is happening inside the function, whether it is transforming data, is it using the time in the function efficiently? And then as we look across all of these, you've got to look at the cost implications of making certain choices. In each of these choices at scale, you need to look at what happens when you go from a really small size in terms of the number of requests, RPS, and throughput to really, really millions or billions of invocations. And so the question is, how do we choose, right? How do we go about making these specific choices? And the answer there really depends on your application. So no two applications are alike in terms of their characteristics. And so for each application, you need to evaluate what are the rate at which my events are flowing in. What's the sort of inflow rate? Then what goes inside an individual event? What is the event made of? What is it trying to signal? What's the size of it? What is the goal you have in terms of your application, in terms of event happening to the output being generated? And then the question to also ask is, what is the implication of falling outside that SLA? So you have to understand what is the impact of going 1 minute beyond your SLA versus 10 minutes beyond your SLA. If it's all the same, or whether there is any cost implication in terms of what it costs your application in order to miss this SLA. And then you should also look at what are the downstream dependencies in my architecture. Do I have a relational database? Or do I have a legacy system that the function is going to call, and whether it has certain rate limits to it, and what implications does scaling have on those downstream dependencies? And then we also talked about ordering and duplicates, and how does the application deal with these particular aspects of event delivery. And finally, what is the budget I have in order for building this application at scale? And how do I look at meeting SLA and addressing the impact curve of the SLA adherence in light of the budget I have for this application. So let's go to each of the 3 parts of an event-driven architecture and look at some examples in which we can use these criteria to focus on what we need to engineer in order to build highly scalable systems. So here's an example of, in the generation area, an event and an application. And this particular application generates a customer. It's a JSON object. And there's another application as an example. It generates a contract file. And so there are 2 choices in which you can generate this particular event. So the first choice is you can inline the content. So you can basically take the file, or you can take the customer up there and invoke Lambda with all of that inline as a part of the payload. And the second choice is you can put all of the event data in a persistent store and then invoke Lambda with a pointer to that particular event. And so there are on face value, it may just like first seem that, OK, choice A is better for app 1, and choice B is better for app 2. But it's not really that trivial. You need to look at all of these considerations when you make a decision. So what is the actual payload size? So even if it is a JSON object, it might really go to thousands of attributes. And so overall, you need to understand what does it take in order to serialize, deserialize this event from your application. What are the implications of moving a large JSON object from point to point? The other question is, if you are storing this event in persistent storage, what are the semantics of it? If you are inlining it, the event payload is going with the event. So intermediate systems that are handling the event are actually containing the payload of the event. And so is that the best way for you to implement your application in terms of access control and security? Or do you want to put it in persistent storage and actually secure the storage itself so that you know who has access to the payload of the event? And then what are the semantics when something goes wrong? What happens when an event gets lost? So if essentially this is a customer lead and the event gets lost due to some problem in the infrastructure, then would you be OK with losing that event, that customer lead? Or would you want to really make sure that the lead is saved somewhere and it's definitely processed rather than being lost? And finally, there is what are the scale limits of all of the components in the system? So if you're storing it in a persistent storage, you need to ensure that persistent storage has the ability to scale to meet the needs of your application as it grows. And lastly, as you bring in new components to your system, you need to evaluate the implications of cost and complexity that it adds onto your architecture. So essentially, the choice here really boils down to these 4 factors, is whether what's the availability, cost, retention, and complexity implications of making that choice. And so if you choose to store the event, for example, your events can be accessible even when, actually, if you inline the event, the events can be accessible even if the source is down. However, if you store it, your events are accessible till they're completely processed by your downstream processor. And then also take into account considerations of there's an extra cost if you're storing the event in terms of data storage, accessing the data, and transferring the data between source and the processor. And finally, when you're looking at all of the other components that you brought into your architecture, do not ignore the implications of the dependencies you have taken and the complexity it adds to your architecture. So when it comes to event routing, there's some choices here. And so the simplest routing mechanism is no routing. Your application essentially invokes Lambda directly. And there are 2 modes in which you can do this. The first mode is simple synchronous invocation. It's a request-response mechanism. And the results of your invocation are available immediately to your application. So the simplicity is great here. But in this model, you as the application developer are managing retries, ordering, error handling, how do you do multi-threading, and what do you do when the application times out. The second mode, and a very popular mode in the event-driven architectures, is the asynchronous mode. And basically, this is the fire and forget mode, where you're generating the event, and now you're basically going to get the results downstream. And in this model, you get some default capabilities from Lambda. You get retries, ordering, DLQ, and a default sort of processing throughput. And we're going to go through each of these in a little bit on the next slide. But you are still managing what do you do when error happens, right? How do you respond to the error being present? And your application still has to deal with duplicates in this model. So a lot of the event sources that come with Lambda are built on this asynchronous model. So an example is if the application generates an object in S3, and the S3 triggers a Lambda function, it's basically having this default behavior. And so what is the default behavior, right? So here are some of the async default considerations to look at. So basically, whenever an event, whenever Lambda is invoked in an asynchronous mode, the system automatically retries twice if your application fails to process that event. And it does it automatically with a system-defined delay. And so essentially, it tries the first time and then 2 other times. And if all 3 tries fail, then the event is discarded from Lambda. Now, what you can do is on the function, you can configure a dead letter queue. And the dead letter queue basically sends these error events, the events that have not been processed after 3 retries, to a SQS queue or as a notification in an SNS topic. And if you are developing applications at scale, our recommendation is you should turn this on so that you don't lose events that that basically are not able to be processed and they have errors. And then when you turn this on, you need to actually monitor your dead letter queue. So on the SQS side, you should monitor the queue length and set up the right alarm so that you know that when your application is running in prod, the errors are sort of spiking perhaps in a particular period of time. And then if you're using SNS, the notification should also be either stored reliably on a persistent store, or you should process it via a function and ensure that you do get delivery of that event. And finally, as described by the retry behavior, there are duplicates. So your application should be ready to handle being invoked multiple times with the same event. And so you should dedupe in your application or have the right keys that help you identify whether this is a duplicate invocation or the first time it's being invoked. So the next routing pattern we're going to look at is Amazon SQS. And essentially, your application here inserts a message in a SQS queue. And Lambda is configured with SQS queue as the event source, and it automatically polls this event source. So in this model, when configured as an event source, Lambda will automatically poll. It does long polling and tries to keep up with the rate at which events are flowing into the queue. So what you need to do is on the Lambda event source side, you need to set the right batch size. So the way Lambda works is it pulls out events in those batches from the queue. And then based on the rate at which the events are flowing in, it ramps up the concurrency of the function. And it tries to go all the way to 1,000. So it goes either all the way to 1,000 or lower if your account level limit is set to lower than 1,000, or on that function you set per function concurrency. But in general, it tries to go up all the way up to 1,000 so that you can process events that are flowing in the queue as fast as possible. And then if the batch succeeds, if your function succeeds, all the events that are in that batch are deleted from the queue. But if it fails, all the messages are returned to the queue. So that's sort of the semantics that you should understand on this particular feature. And so what happens is, if there are failures in your batch, the messages are all returned to the queue, and subsequent batches are going to retry those messages. And so a good practice over there is on the SQS queue, you should set the redrive policy, and then there's a max retry limit on the queue. Once you set these 2 things, what happens is the message is automatically sent to a dead letter queue that is configured on your SQS queue if it is not successfully processed after a certain number of time. So the right sort of pattern over there application-wise is whenever you're processing a batch, if you have partially succeeded in processing some of the messages, you should just go ahead and delete them in your application code so that the subsequent messages that are returned to the queue are only the failed messages, and they will eventually be dead lettered. In terms of throughput, basically, SQS scales horizontally on the production side. So you can generate nearly unlimited TPS based on your incoming rate. And on the consumption side, basically the rate at which you can empty the queue is a function of the batch size, the duration that an individual function takes, or individual execution takes, and the concurrency that you have set on the function. So it's a function of these three particular parameters. So the next pattern we're going to look at is SNS. Here, the application generates a notification in an SNS topic, and then Lambda function would be one of the subscribers to this particular topic. So the advantage of this is this model is that it's a simple pub-sub model where you can now, on the consumption side, fan out to millions of subscribers. And so you can publish at a very extremely high rate and deliver the notifications to a lot of consumers, Lambda being one of them. Again, in this model, ordering is not guaranteed, so you need to be prepared for at least once delivery. And then there are two components to delivery of the event from the SNS side to the Lambda side. The first component is basically getting the message from SNS to the Lambda's intake queue, and that is highly reliable. The SNS will make up to 50 attempts over 12 hours and ensure really the delivery of that event. And then once the event gets into the Lambda queue, it is processed with the default behavior. So this is the same async behavior that we discussed a little earlier. And then from the scale and processing perspective, the one thing to look at and remember is that in this application pattern, every particular notification will generate a single invocation of Lambda. So if there is no batching here in this model, and so if you desire to batch events or notifications, you should really put a SQS queue ahead of SNS, and then apply batch processing on that SQS queue. All right, so let's go through some of the considerations when it comes to event processing. So one of the things to kind of pay attention to on the event processing side is the concurrency with which you process events. And here, one thing to really pay attention to that sometimes a lot of developers get stumped with is they feel the rate at which you invoke Lambda, the TPS, the invoke TPS is what is concurrency. So it's not really that. Concurrency is really how many Lambda functions you have running, how many instances you have running at a single point of time. And so it is essentially a cross product of the TPS and the duration for which the function runs. And estimating this is not straightforward. You need to look at what is the invoke rate for your function, what is the duration a function runs, and what are the distributions of these things at mean and at various percentiles. And the thing to pay attention to here is that if you take peak numbers for everything and you multiply them all, it generates a really high number. And so this chronic overestimation is a problem that we see all the time. People suffer from when they're trying to estimate how much concurrency they actually need when their application scales. But then you also want to guess correctly, because if you guess it wrong, you are going to have, it has performance implications on your application. And so a good way to estimate concurrency is you start with your peak TPS, and then you multiply it by your average duration. And so that gives you a good starting point in terms of what is the concurrency you need when your application scales to its full level. And then you should basically start there and run a load test. And then there are two metrics, concurrency and duration, that you should monitor through your load test. And those will give you an idea of what's the max concurrency you actually need. And in general, basically, you can open a support ticket, and this is we can set the right concurrency limit for you in order for you to experiment with and just get this right. And then there are two parts to setting the concurrency. There is the account level concurrency limit, and this whole calculation is all about the account level concurrency limit. And we're going to just talk in a moment about what the per function concurrency limit is. So per function concurrency, it's a limit. It's not a reservation. This is something, again, lots of folks get wrong. It's a subtle difference, but a very important difference because it really is not reserving anything for you. What it is that it is the maximum concurrency to which a function is allowed to scale to. So the real intent of this feature is that we want to be able to control how much a function scales so that you can protect some of the targets you have downstream. So if your Lambda function is accessing, say, a legacy system that has a TPS limit of 20, and your application scales to 1,000 instances, is basically going to overwhelm that system, right? So you want to be able to use the per function concurrency to set the right limit on an individual function so it does not overwhelm downstream systems. The other use of per function concurrency is it's a kill switch. You can use it to throttle a runaway function. And so if you set it to 0, all the instances from there onwards will not be able to be generated or instantiated. And so all the invokes thereafter will be failed. The other side effect of setting the per function concurrency, and probably the reason why it is being sometimes confused with reservation, is it has the effect of reducing the effective limit available for all the other functions. And so, for example, if your account level limit is set to 1,000, and the two functions in green and yellow are set to a per function limit of 100 and 200, then everything else in the account can only go to 700 concurrency. So the benefit of doing this is that it prevents noisy neighbor problems. So for the green and yellow function in this example, you have the room to go to the stipulated concurrency that is set on that, those functions. And so the guideline there is, if for the SLA-bound parts of your account, you should set the per function concurrency. And what that lets you do is, whenever your account has unpredictable load, what you're assured of is that those particular functions have the room to be able to go to the concurrency that you have configured. And then the other sort of guideline here is, after you set it on all the SLA-bound functions, if you're running out of account level limit, you should evaluate getting a limit increase. And so do the math with us, open a support case with an increased limit request. If the sum total of all the configured per function concurrency limits is exceeding your account or basically leaving no headroom for the rest of your account. The next topic that is also of interest here in terms of excuse me, of event processing is velocity. And so velocity is the rate at which your application scales from steady state to its top. And so here you have 3 examples in the top, and they are all going to 1,000 concurrency. And so the top one is just a slow, steady ramp up. The middle one just goes from its steady state to 1,000 immediately, and then there's a spiky workload. So you really need to know which type of workload your application is, and what type of throughput goals, or what type of goals you want to achieve, basically with Lambda. And one of the key things to think about is what is the goal in terms of the rate at which the overall work needs to finish, like throughput, and if you have individual goals from event occurring to the event being processed. So this is the event to process latency, basically. Now, there is a fixed predefined scale behavior that Lambda has, and it basically follows a token bucket mechanism. Whenever your application invoke rate increases, Lambda grants you an initial bucket of concurrency, and then it ramps up at a certain rate. So depending on the region, when your application is trying to scale up, it goes to either between 500 and 3,000 concurrency immediately, and then it goes at 500 a minute. So the slope of the ramp is 500 a minute, and then the initial grant is really dependent on the region. And then the part to here think about is, what's the impact of a slower ramp on your application? So generally, if your application retries, backs off, and retries, and it's an asynchronous application, there's really no impact in terms of what it on your application or end user experience, right? So really think whether these limits that are there in terms of the ramp and in terms of the initial concurrency grant are something that you need increased, or whether that is something that your application is just resilient to by virtue of backing off and retrying. So the last topic we're going to talk about is what an individual function does. And so your overall application scale really just depends on the behavior of an individual function and its profile in execution. And so the right way to think about Lambda is that you should use your functions to do transforms and not really do transport. So if your function is basically simply moving bytes from place A to place B, Lambda is not the right solution. Most of the time in your function is spent on waiting for I/O, and you're paying by the millisecond, and so you really don't want to do that. The other thing in terms of scaling is batch size matters. So make sure that you set and tune your batch size so that you can achieve the optimum throughput. And so it's really a trade-off between concurrency, how concurrent you go, versus how long an individual function runs, and what's really just the right mode for you in terms of your application. And here, also evaluate kind of how long an individual function runs. This year also launched a longer running function, so functions can now individually go up to 15 minutes. And that's something to consider in terms of how you tune your batch size and throughput. The other thing to also play with is the memory size of an individual function. And so CPU that is allotted to your function is proportional to the memory size. And if you are greater than 1.8 GB in terms of memory size, you also get the ability to run multiple threads. And that may be beneficial for you in your particular application. And so lastly, I'll just make the same point I almost pretty much made earlier on this slide, which is in terms of Lambda, whenever you are waiting for something, it's not the best use of that resource. So if you are spending time just waiting for a document to be OCR'd or waiting for a slow API to complete, you're not really making the best use in terms of the compute dollars that you've spent on Lambda. And so if you find yourself doing orchestration in your code, that's not the best use of Lambda. And so you should really look into AWS step functions, which will help you orchestrate a bunch of capabilities and will give you this very beautiful state transition diagram, and you can manage orchestration using AWS step functions. So with that sort of overall guideline, we have a little bit of time now for, I want to bring up Mick here from Mapbox, and he's going to give us a real-world overview of how they implement some of these capabilities in their application. Okay. Mick.
Thanks, Amit. So, yeah, I'm Mick. So as Amit mentioned, I'm Mick. I work at Mapbox, and so I'm going to just use satellite images to make this more interesting, since sometimes there's not a lot of diagrams to go with this. And so in this section, what I want to do is kind of highlight a few of the things that Amit talked about in a real-world pipeline that we run at Mapbox, talk about a few of our additional use cases that we have at Mapbox to give you some variety of how we use Lambda at different scales and different shapes, and then give you a couple things that we've found to look out for and how we've worked around that. So just a quick introduction to Mapbox to set up the use case. Mapbox is a location services company. We're a platform really for applications that want to take advantage of customizing how location is used inside their application. So that can be how the map looks, how it's styled, what's on it, how the search works, how you get directions from A to B. And we have hundreds of millions of customers, hundreds of millions of users around the world. And this, since we are predominantly an API company, translates to tens of billions of requests per day. We were here at reInvent. I remember when Lambda was first introduced, we were in the audience and we were like, hey, we run a lot of JavaScript and this runs JavaScript. We are totally going to use this. but little did we know exactly how many uses that we would find for it. So Lambda has been super useful in stream processing. We have a live traffic product. So when I say traffic, I actually mean cars on roads. And we use Lambda as part of that stream processing. We use it in Dynamo streams, actually having like chain sets from DynamoDB. We've used that to create replication from DynamoDB before that was a feature. API Gateway has let us use Lambda for some internal purposes, for also some post hooks. Has just kind of expanded where we can use Lambda. When S3 introduced event notifications, that kind of, it really gave us another hook where we could use Lambda. And you'll see that's actually the trigger that I'll talk about in the pipeline today. But this really is, it's really part of the broad ways that Lambda has been increasing the way the different event triggers. And this has made Lambda more and more useful because Lambda is, I think of it as really the thing that you can use to bring all the other resources of AWS together. So sometimes that means in a CloudFormation template, if there's not a feature that's already supported by CloudFormation, or if there's a feature that we want to add because it's a resource that's actually a custom resource, something that is specific to us, we add it via Lambda. And then scheduled events pretty much speak for themselves. Running things every 5 minutes isn't really massive scale. This is a graph of, as far back as CloudWatch had, of our Lambda invocations. The takeaway here is in about the last 13 months, we've doubled our Lambda usage. This doesn't really go back to as far back as I wanted it to go. But we've kept steady or increasing our Lambda usage because we found it very useful. And that's because we start a lot of projects in a way that I would say we think in Lambda. What I mean by that is we start out by piecing together something as just a series of functions and really only take that, use that as like a prototyping or like a proof of concept mode. Sometimes that ends up being exactly where we scale up and that proof of concept turns into an actual production system. Sometimes we can just reuse that same code, those same functions in another system as we actually need different resources. So let's get to the actual pipeline so we can talk about some more specifics. So I want to talk about log processing. One of the use cases that we have being a company with a lot of API requests is a lot of API requests generate a lot of logs. And those logs are insightful for us. It helps us track usage of the platform. It helps us analyze what customers are actually doing with our product. And really, we only get the full picture of that from our CloudFront logs, from those edge requests. So in order to bring in those tens of billions of requests every day and be able to do that in a quick fashion so we can also use this for debugging, for errors, and perhaps for analysis of something that's very timely, we use Lambda. Now, in order to actually do the querying of that in an interactive fashion, we use AWS Athena. This isn't an Athena talk, so I will be brief in just highlighting this. But a couple things to know about it. Athena lets you take a SQL query and directly query files that are on S3. It does this in a highly distributed fashion, enabling you to do basically interactive queries on flat files on S3. But the catch with Athena is in order to make it more performant and also to keep costs down, it really matters how you shape the data on S3, both in how you actually do the key structure for that data and also in the format that the data is stored in. So that's the first step of what we want to do with CloudFront logs. Because our CloudFront logs, as I mentioned, are tens of billions of requests per day. This translates to 20 to 30 terabytes of data per month. And CloudFront delivers this on one path on S3 with not a lot of prefixing, and they deliver it as gzipped tab-separated values, TSVs, and that's not the optimal format for Athena. We want a little more structure in the key space, and we also want a better, more optimized format for the data. But the other thing about this is not only do we have traffic patterns, just daily traffic patterns of when people are awake on certain sides of the planet, but also CloudFront does like a flush at the end of the hour for any remaining logs. So we actually see up to like 3x spikes of that traffic. Now we don't want to be provisioned to 3x spikes all the time. So one of the things that Lambda lets us do is seamlessly scale up to that. Now, someday, I hope, I come to reInvent and CloudFront says, hey, we're just going to deliver the logs in the exact format that you wanted, and you get to delete this. But even when that day does come eventually, we do more than that. We do more than just a little bit of reshaping of the data. We also add our own business logic. So in Lambda, we take advantage of being able to parse some of the complex queries that are in there. As everyone has a lot of information baked into your URLs, into your requests, we parse some of that out, so downstream it's easier to query. Do some lookups. An important thing to note here about the lookups is these can be expensive in terms of time. Parsing a lot of log files in JavaScript is not the fastest and most performant thing ever. And we'll get back to cost and ways that kind of impacts things. So no AWS talk is complete without a diagram of all the complex resources involved in a pipeline. While we do definitely have pipelines that are more complex and stacks that take advantage of many resources, one of the most powerful things I think about this stack is it has so few moving parts. So for doing this log ingestion, all of the logs are delivered to S3. From S3, an event notification triggers a Lambda. That Lambda reads that file off of S3. It does the parsing and writes that back to S3. One of the things that I think also sometimes gets glossed over is just how deployment can work with Lambda. So, and it's important because you're going to deploy your Lambda function a lot of times. You want to have this be very seamless and very fast. So we use CloudFormation for all of our deployments across Mapbox. And in Lambda, we actually, so when we push to GitHub, we trigger a Lambda that then triggers code build to build an artifact that actually bundles up all of the dependencies for that function into a zip file, puts that onto S3, named with the git SHA in the name of that file. And then a deploy is just as simple as updating the git SHA on that CloudFormation stack. So really can just streamline the entire process, also with Lambda. As I looked into this talk, one of the things I was going to highlight is the actual Lambda code, right? So for this log processing pipeline. But you know what? When I started pulling things out of it, it's just all our business logic. And that's actually a great thing. Because rather than a lot of orchestration or a lot of handling of concurrency, really this is just focused on our own business logic. So loading a file, parsing it, writing it back to S3. The one thing that I will note here is in order to be more efficient with resources, both in terms of speed and in terms of memory, we do stream the file entirely. So we use node streams. So as we read the file off of S3, we're already starting to parse it. We're already starting to write it before we even have read the entire file. Now, things are going to go wrong. especially if you're streaming a file, parsing it, and writing it back to S3, there will be network interruptions to that. Lambda automatically gives you retries, and that's important to note. So you're already going to get 2 retries on an event like this. So this is triggered via SNS from the S3 notification, event notification. And so you get 2 retries. Maybe the first one fails. That'll show up as an error if you're looking at your Lambda errors. And maybe it succeeds on the next one. Maybe it doesn't. What's confusing there, or what, like, the state that you don't actually know, is whether or not that specific file has succeeded. And this is where, as Amit mentioned, the dead letter queue is super useful. So especially as you're building things at bigger and bigger scale, you're going to have many files going through your Lambda, and being able to track down individual files that are causing problems, or being able to replay those problem files to your Lambda is going to be really help you debug things. It's also going to help you in monitoring. So as I said, you might see a spike in Lambda errors, but maybe all those files actually got retried successfully. But when you have a dead letter queue, you actually know if a file went through all the retries and wasn't successful. So you actually know that something is wrong, things are not being retried successfully, not making it through your Lambda. Now, cost is just resources times duration in Lambda. So you have 2 levers in order to bring the cost down. And as I mentioned, one of the ways we do that is by keeping our footprint a little lower. So with node streams, we're both trying to do things a little bit faster by already doing some processing while the data transfer is in process, but also we're keeping a lower memory footprint. So instead of having to load the entire file in memory and have a Lambda that automatically costs more because it has more resources, we're able to reduce that cost. Lambda does a lot of the scaling work for you, which is great, but with great scale comes a responsibility to your coworkers not to impact everyone else's work. So I'm guilty of that. Definitely have done that before. When you have many Lambdas in an account, we have thousands, it can be a little bit tricky to manage those resources. And what can end up happening is you suddenly have one Lambda that someone set up that gets very popular for whatever reason, and that can cause throttling across your entire account. Now, the ways around this, the ways to fix this, are one, to set up to actually set up limits per Lambda function, right? So this is something that Amit mentioned before. And these are, they're similar to reservations in that it actually does reserve a portion of your overall Lambda invokes for your account. And this is where you should email Amit and get a higher limit. But it also gives you, so I suggest doing that, especially for functions that you want to have like an SLA around, right? So there's going to be very important functions in your account that you want to make sure always have enough resources. So setting up that reservation for those. But then also being able to track down noisy Lambdas is important. So one of the things that we've built is really just a script that goes through all Lambda invocations to look for anomalies. We've only had to run it a few times because we've now managed to really bring down the concurrency of our account by using the per function limits. Now, another trick in order to get more out of your Lambda function, and this wasn't obvious when we first started using Lambda, but Lambda reuses the container between invocations, but not just the container, also the process. So if you're writing your Lambda in JavaScript, and you set a global variable, that's going to get reused, actually, in the next invocation. Possibly. There's no guarantees, right? Because new containers are going to start, your Lambda is going to scale at times, containers are going to cycle. But you can take advantage of this, just as Lambda overall is taking advantage of this to make the service faster, you can take advantage of this by caching some data. So in our log processing, we cache certain lookups to make the overall processing faster. You can also use a little bit of disk space for this too. It's an option to give you some flexibility in being able to bring down that cost. Now, we didn't initially use SQS-based Lambdas because this was a feature that was introduced earlier this year. But one of the advantages that we've seen and why we've been migrating some of our Lambdas to use SQS is it gives us another lever to deal with concurrency and spikes. So if you look back at actually just having your Lambda like throttle at a certain, say like 100 concurrency, right? If your Lambda starts throttling at that, throttles are errors. Like those events are getting retried, and maybe if you still have enough concurrency left, they'll be retried successful. Maybe not, they'll end up in your dead letter queue. But SQS gives you a bit more control over that concurrency and the ability to build up a bit of a queue. So if you do have just a sudden backlog, or in our case, we've used this for doing actual backfills. So we want to actually load up a lot of work and have Lambda process it at scale, but not too much scale. It can be useful for that. Of course, with SQS, you still have the ability to set up a redrive policy on the queue. So you still have that dead letter queue. You also have more control over the retries itself. So instead of just 2 retries from Lambda, you can say, I want to boost that a little bit. I don't want to be paged in the middle of the night. I want it to retry a couple more times. So yeah, we found Lambda to be a very flexible product, something that we were able to build a lot of different pipelines around, not only log processing. I use that as an example because it's one of the easiest ones to fit into like a short talk, but also more complex use cases that actually involve a series of chained Lambdas and many more things. But the important things that we found in building those is the monitoring and error reporting. Like I still can't emphasize DLQ enough. I'm sure though you disagree because I've said that a lot. And then the other important thing that I would say is a good takeaway here is Lambda can become an expensive product. If you use it in the right ways, it can be a very cheap, fast way to iterate on code. But at the same time, if you just crank up all the resources and do things that have long durations, it's not as cheap as other ways of doing compute. And with that, I'll pass it back to Amit. Thanks.
Thank you, Mick. What an exciting use case they have here. So whether it be like mapping the world, whether it be doing trillions of stock trade validations, you can build serverless applications at scale on AWS. And we have a rich portfolio of services on AWS that helps you build this particular sort of applications. And it is a world full of choices. So really, what you need to do is to make the right choice in terms of the right tool for the job. And basically, the right way to build scalable systems is to just go part by part in your architecture and look at the 3 major areas of generation, routing, and processing, and go through the considerations on each of these areas in order to identify what are the likely pitfalls that you might run into. And then finally, serverless pricing makes it easy. you can experiment a bit, and then if you get it wrong, the cost of retrying and overhauling is not really that much. So you can really try, tweak your architecture and deploy it over and over again. If you can predict something, it will just shorten your overall cycle. But if not, you should just relax and try to basically figure it out as your application scales. So with that, this is the last breakout repeat of this session. And the other session I highly recommend everybody go to is this leadership session. And this will just give you an overview of the serverless landscape, how we are thinking about serverless on AWS, and what are some of the innovations that are in the pipeline. And so this is tomorrow at noon in the Venetian Theater. And you will see some of our leaders come out there and just give you an overall lay of the land here. With that, thank you so much for attending this session. And here is our contact information. Do let us know if there is something we can answer. And definitely complete the mobile survey. And we'll be here a few more minutes after the talk if you want to chat with us. Thank you.